release you close to the surface of a planet. And that's what we talked about. You would experience an unbalanced force in this direction. And that net force would be equal to ma. Now, if there's no normal force and you were just dropped or released near the surface, well, that force would be the mass of the planet, the mass of you, g, and separation distance, which we said was basically the radius of the planet. And that'd have to be equal to, well, the mass of you. You are the one being dropped. And that would be times the acceleration due to gravity. And this is how you could find the acceleration due to gravity on any planet, not just the Earth, correct? You would just need to know the mass of that planet and its radius. So not particularly hard. Now we could do the reverse. We could find the acceleration due to gravity of you, on the Earth due to you, by reversing this and canceling out the mass of the planet, but that is going to be a really small number, as we discussed, and not particularly reasonable. The Earth isn't going to move that much compared to you, but you will experience a lot of acceleration. But this is how you figure it out for the Moon or Mars or Venus, wherever you're going to be trying to set down maybe a space probe. It's probably good to know what the acceleration of gravity is going to be when you get there. You can probably see the obvious implications. Now, let's say, just for argument's sake, that we give you a sizable velocity in this direction, knowing that there's going to be a force in that direction. Sizable velocity means that you would be moving this way, but the force would be changing your direction. You'd be a projectile. But this is a projectile on not level ground. If I chuck you fast enough, the curvature of the Earth will fall away underneath you as you come to the ground. Again, still a projectile. If I can chuck you fast enough and give you enough velocity, then your velocity should be great enough that the curvature of your fall matches the curvature of the planet. That'd be an orbit. A stable orbit in which your velocity precisely matches the radius of curvature around the planet. So, consider a simple concept of an orbit. Let's say the orbit of the Moon around the Earth. And I use the Moon mostly because we know things about the Moon, and we can use those things in our discussion. So consider a circular orbit. The Moon is in an almost perfectly circular orbit around the Earth. It has a very high eccentricity. Now, is there anybody here who was in astronomy last year or this year? Yes, of Kepler's 3 laws, there is the fact that all objects orbit in an ellipse with your gravitational elements, whatever your heavier object is, at one of the foci. There's a ratio between the period and the axes, and it's a square to cube ratio. And the object that's orbiting sweeps out equal areas in equal time. Now, first you should know that a circle is an ellipse, right? If you know how ellipses are rated based on eccentricity, which is a ratio of the semi-minor axis to the semi-major axis. So all ellipses have an eccentricity that is 1 or less. A circle has an eccentricity of 1 because its minor axis and major axis are the same size. And that also means that in a circle, the foci overlap and there's just one center. And that's what makes a circle. A circle is a type of ellipse. Now, that being said, we're going to study circular orbits for a couple of reasons. And one of them is that to be in a circular orbit means that you will have a constant velocity, unlike being in an elliptical orbit where your velocity is changing. That's the equal areas and equal times conversation, which is actually a consequence of conservation of angular momentum. And we will get to that second semester. We don't have that now, but the angular momentum of the system is conserved, and that's why the velocity, it does what it does. It also has to do with the fact that when you're closer, the force on the object is greater, therefore it moves faster. And as it gets further away, it's being slowed down by that same force. So when it's further away, it's slower. And it's a play between the gravitational force and the acceleration of the object. Since our object has a force that's towards the center, by definition, this is a centripetal acceleration, so there must be a force towards the center. It is perpendicular to the velocity, which is tangential. So in a circular orbit, the velocity has to stay constant because this force can only change its direction, it can't change its speed. So we are looking at an orbit that obeys not only Newton's second law, but a specific version of Newton's second law, one in which the acceleration is the centripetal acceleration. Now that force is provided by gravity, which means that that force has to do with the mass of the planet, the mass of the satellite, the acceleration, the universal gravitational constant, and in this case, r squared, which represents the separation distance. Spelled distance wrong. We should do better, Mr. Shelton. When we say separation distance, we're talking the center of mass of one object to the center of mass of the other. On the other side, we're talking about net force equals m v squared over r, where v represents the tangential velocity and r represents the radius of curvature. Today, for most of the class, we're going to assume the separation distance and the radius of curvature are the same for most of class. But that's an exaggeration. That's not true. And you have to be careful about when you can and can't accept that. That can be said to be true when the mass of the planet or the mass of whatever's at the center is much greater than what you consider the satellite to be. But when those two things start having appreciably similar masses, then you have to start taking the center of mass into the system into account. The truth is, objects like this don't orbit about one object. They orbit about their mutual center of mass, some point somewhere in the middle. So the Earth is going around this point, and the Moon is going around this point. Basically, the Moon causes the Earth to wiggle in its orbit because they have an appreciable relationship between their mass. Now, if we were comparing the Earth to the Sun, well, there's not really a comparison. The mass of the Sun is much greater than the mass of the Earth, so the Sun is at the center and the Earth goes around it, and the Earth does not cause the Sun to wobble. There's no real appreciable center of mass there to take into account. Jupiter, on the other hand, big enough to cause the Sun to wobble, they do orbit about their mutual center of mass. In fact, I just want to talk to you about some simple situations, and this is one of them. And I want to add one more thing to this because it comes up a lot. We're usually way more interested in how long it takes something to orbit and less interested in how fast it's moving when it's orbiting. So it's not a bad idea for us to recall something from earlier in the year, that the velocity of an object traveling in a circular orbit or in a circular path would be equal to the circumference of that path divided by the period. And although I guess I use a P for period in astronomy, we will use a capital T because it's a period of time. So notice that I left a small r on that side. Those formulas deal with radius of curvature. I left them small r. And the things that deal with separation distance, I put big R. Everybody good? Now, for this example, we're going to say for the Earth, Moon, that these are the same. They are not. We will redo this problem when we want to take that into account. But for today, we'll say that they're the same. Ready? All right. There are 3 basic orbit questions that you should be able to answer. And they go like this. You should be able to figure out what the tangential velocity is. That's a common question in an orbit question. Another common orbit question is to figure out the period of the orbit. And another common question is, if you want to put something in a specific orbit, what would that orbit's altitude be? If you look at your homework, I've given you all three of these kinds of questions. Be careful with questions that are about altitude. Altitude is defined as the distance from the surface. So if we're talking about the altitude of an orbit around the Earth, we're talking about the distance from the surface. You will have to deal with that difference between the distance from the surface and the radius. So the radius, r, that we've talked about here, and the capital R, separation distance, are different things. Altitude is a third thing. So if we were looking at this system, exaggerated as it may be, there's the separation distance. There's the separation distance, which would be that line. But then there's the altitude, which would be that line, the distance from the surface to the center of the moon. Everybody understand the difference now? So, again, this would be capital R, but this would be the altitude. I believe one of your questions asked about a geosynchronous or geostationary orbit and asked for the altitude of that orbit. By saying it's geosynchronous or geostationary, I'm giving you the period, 24 hours. And I'm asking you to work backwards and find, for me, the altitude. You'll need some information to do that. But let's talk about what we would have to do to find the velocity of the moon first. Looking at the information that's presented here, if I were to kind of fold that over to the side, I think most of you would agree that we could start with saying, well, the mass of the Earth, mass of the moon, and g, all over the separation distance squared, would have to be equal to, now the m on the right side, the part that's in MA, is the mass of the object orbiting. So when we use this, we're talking about that m being the thing that is doing the orbiting. So in the case of this problem, we're talking about the mass of the moon. We're talking about the moon's orbit. But instead of A, we're going to put VT squared over R. Now, if we want to find the velocity, first we have to decide, are we dealing with a situation in which the Earth is at the center and we're dealing with an object that has the same radius as separation distance? And I already said that's what we're going to do. So replace this with capital R to make it the same type of variable, and that means that they're both going to be the separation distance. Now, I hope you notice that we can cancel a couple of things out. Do you notice that? So mass of the moon gone, and one of the r's is gone, leaving with mass of the Earth, g over r equals the tangential velocity squared. So we'll just take the root of both sides to get a calculation for the tangential velocity. And you should be able to derive this on your own. It is not uncommon to be asked to derive this on the exam. Pretty simple. So figure it out. You need some information, I think, don't you? So mass of the Earth, I've already given you, but 5.96 times 10 to the 24th kilograms. And you'll need the Earth-Moon distance, which is 384 times 10 to the 6th meters. Yeah. Now, is that fast? The problem is that, how do you define fast? I mean, in astronomical speeds, it's not that fast. I mean, ultimately. Now, compared to things that we're familiar with on the Earth, pretty fast. Speed of sound, 330 meters per second. So if you want to send something to the moon, you will have to get it up to that speed in order to be synchronized with the speed of the moon, right? So this is bullets from rifles, but not bullets from pistols. That's how fast the moon's going. But again, I don't know if that's particularly fast. I want you to consider something that you've probably never done before. The problem we just did here, so you should tell me, what is the period? And you already know this. It's 28 days, full moon to full moon. So figure out what the period is from this. If you don't know what I'm asking, just look over here. I'm circling something. Hustle, we're running out of time. I've got 12 minutes. I need them all, and we got more to say. Just got to do a little bit of algebra. You're going to put your velocity in from a moment before. R is still going to be 384 times 10 to the 6th meters. But this gives you a value in seconds because we're taking meters and dividing by meters per second. So to have it make meaning, you should convert it to days, which gives you 27.4 days. Now that's not the time it takes to go from full moon to full moon. It's 28 days from full moon to full moon. Are we making a mistake? We are. I said it at the beginning of class. What is the mistake we're making? Yeah. We're making an assumption. So we're going to have to do it the right way. But the answer we get doesn't fix the problem, and you're going to see why. It actually suggests that the time it takes to go around the Earth is shorter, not longer. So does anybody know why this isn't? How long between full moons? Not because the solar system's moving, no. It's because the Earth's moving. How long does it take? It takes 1 whole month, right? In that time, the Earth has moved. So if I were to use my busted up Earth as our example, which pains me because it's all broken, but we'll just take the bottom half. And let's say that Iron Man here is the moon. Say the sun is the back of the room. It takes 27.4 days to do this, right? This would be full moon when we're behind the Earth, right? So 27.4 days, but now the Earth has moved 1/12 of its orbit. So if we want to get back to a full moon, we'll have to wait a little longer to line up with the sun again, right? Because the Earth is going around in its circle. So it takes a little bit longer to go full moon to full moon than our actual orbital period. It's amazing the number of things on the Earth that have a 28-day cycle. Migration of lobsters, spawning time for a ton of aquatic animals, a bunch of lifeline things on the Earth, pollination times for different flowers. It is bizarre, but not bizarre. They all evolved, and they all had to fight for resources. Adapting to when it was going to be bright at night was an adaptation that was successful for plenty of creatures. So having a 28-day cycle built into the evolution. A weird thing, the same side of the moon faces the Earth the whole time. Its rotational time is the exact same amount as its revolution of time. Right? The moon is spinning, and it spins in perfect synchronization with its orbit around the Earth. That's weird. It's called a tidal lock between the Earth and moon. And luckily, the Earth doesn't have the same problem, right? Or else our day would be 27.4 days or 28 days, depending on how you look at it, how we would define a day. But why the moon got tidally locked is kind of a mystery, which is why we see the same face of it all the time. But we're pretty happy it's there. It churns the oceans, makes the tides. Again, so many things are reliant on just the moon's gravitational pull on the Earth. And I can name about a dozen, but those are enough. Not to mention what the backside of the moon looks like. Horribly potted with massive craters. More things have struck the moon than the Earth. The moon protects us and has done so successfully a lot. But I want you to do one more thing. And I think you can do this. I think this class can do this. We'll see. Because we only have 5 minutes to do it. And it's pretty straightforward what I'm going to ask you to do. But we have this relationship, that's the force that's causing a centripetal motion. And there is a relationship between how fast something moves and its period of rotation. Let's skip the middle step. Let's see if we can find the relationship between the period and the other variables so we could find the period directly without having to find the velocity first. Does everybody understand what I'm asking to do? We did it in a two-step process. Let's do it in a one-step process. Let's mash all these things together. Now, you guys who are sharp, just get to it. For you guys who don't know what I'm talking about, let's play like we're doing the mass of a planet and the mass of a satellite. We'll use those symbols for our things, and we'll say that separation distance and radius of curvature are the same. So with that, I'm going to go mass of planet, mass of satellite, g over separation distance squared equals mass of satellite times vt squared over separation distance. Now I can make my simplifications by canceling out the satellite and one of the radii, and I get mass of planet times g over radius equals, I only have vt there by itself, but I'm going to sub in 2 pi r over t. See what I've done for my substitution? I've done this substitution right there. Now, if I expand, Kepler was a mathematician. He looked for patterns. Newton was a theorist. So although Kepler didn't know why this was true, Newton did. Right? Kepler's law. Now this works for circular orbits. It will also work for the elliptical when we take a look at it, but do you see period squared to radius cubed? All right. Now, it also means you could figure out the period directly. It's also how you answer several of the homework questions that have to do with orbits, especially those that have to do with radii. Now, you should try something silly like maybe find the period of the Earth around the sun, prove that this works. You're going to need something like the mass of the sun, which is 1.99 times 10 to the 30th kilograms. And you'll need the Earth-Sun separation distance, 149.6 times 10 to the 9th meters. There's only 1 minute left, so that's probably not enough time. But if you convert your answer here to days, you should see why we have leap year. We've talked about why already, but now you can prove it. And this will be easy to do. Let's say we're looking down on the Earth, so ice cap here, whatever's left of it. We're looking down, trying to find Santa Claus. And this represents a point at the equator. Is that good? Yeah. Radius of the Earth is 6.38 times 10 to the 6 meters. How fast is, if the Earth is going this way, how fast is that point going? You know how long it takes the Earth to go around once. I mean, if we use VT equals 2 pi r over t, You should be able to give me a value in meters per second. Do you understand what I'm asking you to do? Not a hard question. 464 meters per second. Now, I want you to think about that for just a minute. That's how fast, well, not us. We're not going that fast because we're not traveling in that big a circle. That's how fast the equator is going. But still, pretty fast, wouldn't you agree? Yes. I mean, do you understand how we can get such amazing weather when every mountain range is a huge scoop that is just stirring the air? I mean, that's how fast the surfaces of the Earth is traveling. There's no getting around that. If the Earth were to suddenly stop, all of us would go flying towards one of these walls at 464 meters per second. Just because the Earth stops doesn't mean we would. All right. You guys are super smart, and we can go right back.